This model kind of seems to not have really been on a lot of people's radar, but it's a pretty cool model called UniAudio. They claim it's a foundation model, but it's just like it's a model that does a lot on an audio model that does a lot of different tasks, or at least they train it on a lot of different tasks. It's open source, which is awesome because some of the best audio models are not really open sourced. Like this one, VoiceBox by Meta is not open sourced, which is kind of annoying. And I thought that was going to be a really cool model. But this one is open sourced, and it also does more tasks, and also does more tasks than VoiceBox, which is cool because I thought VoiceBox was a really cool model. Yeah, I mean they have a page of a ton of tasks. You have 0-shot text to speech, so you give it some text, you give it the prompt.
But short, happy bits of laughter that
So the person you want it to talk as, and
It is 16 years
generates it in
since
that
John
voice.
Bergson died. It is 16 years since John Bergson died.
And that's pretty standard. Cloning someone's voice, that's also pretty standard. And then they have a ton of other tasks. This one was pretty cool. This one here, where is it? Yeah. So there's like mixed speech.
He began a confused complaint against the wizard.
And then you give it the prompt.
They then renewed their
So the
journey.
person you want to extract the speech from.
He began a
Then it
confused.
extracts it pretty well. And then there's other tasks which are not speech related, like sound tasks. And the tasks that are not really speech related don't sound as good, and you'll probably see why in the model. You could probably guess why. But let's see, like this one here, a bird chirping should be pretty easy to generate, but it doesn't sound that good. Like you can kind of hear it, but it doesn't sound super good. And then music also doesn't sound amazing as well. You can kind of tell there's a little bit off with it, but I mean it sounds fine. There's definitely a lot of improvement, but I do think it's a really good start and a really good idea. So yeah, let's get into the paper. So it's very much an engineering paper, just trying to get this thing to work. Basically, what they do is they say they want to just take a bunch of audio sources and throw it through a single model. So yeah, they basically have all these tasks here. So text to speech, voice cloning, sound, music, they have all these tasks, and they basically want to have a single model that processes this. And the way they do that is, if we look here, they have this table of tasks. So text to speech, voice conversion, not voice cloning, my bad. Text to sound, text to music, and they have all the conditions. So for text to speech, you would want to condition your model on the phonemes and the speaker prompt. So your phonemes would be the text, and then the speaker prompt would be the speaker you want to speak in, and the output is speech. Voice conversion, you have semantic tokens, speaker prompt, and speech. And notice how all the outputs are just audio. So they basically say, as long as you can encode the conditions in some way. So you have some model that can encode these conditions. For textual description, maybe that's like or maybe that's like a transformer, an LLM that's already trained, and you just encode it. Maybe like BERT T5 UL2, something like that. Maybe you use something like encodec to, or some sort of codec to encode the audio, like noisy speech or a speaker prompt. And as long as you can encode that, then the output is always just going to be audio. So if you just train a model to generate audio, given some conditional information, then you're good. So that's what they do. They basically say, we don't care what the conditions are, that is arbitrary. Whatever task you want, as long as you can encode it, we can generate this as, we can make this an audio task where, given some conditions, we generate the audio. And yeah, let's just get into how they do that. So to start, let me get this over here. So to start, let's say we have a audio sequence. So we have some long audio sequence, and we want to encode this. So the way you're going to be able to generate audio is, first you need to be able to represent that audio in some way the model can use. So they use a transformer because transformers are, I mean, they're really easy to train. You can stuff a lot of data into them, and they do amazing things with that data. They're really good at autoregressive decoding. So why not model this task as an autoregressive decoding task? But that requires you to tokenize the audio, which you do with a codec. And specifically, you can do residual vector quantization on that. So let's say we're given a audio stream. So this is going to be the audio we want to produce. And this audio stream X is of shape, this will be in R. So this is a continuous, or this won't be in R. This is a continuous representation between -1 and 1. So each part is between -1 and 1. And you have D by F of S frames. So what was, yeah, so you have this, yeah, this is your X, and you can basically represent your audio between -1 and 1. So you just kind of squash it, you normalize it, and then you have D by F of F frames, where F of S is the sample frequency. So F of S, maybe that's 1600 48, or 16,000 48,000, and this is just how you sample your audio. So you need to sample it in some way, and then D is the number of sampled frames you have. So that would be D. So this is D by F of S, and then you can kind of encode this and decode this. I'm guessing they use something like encodec to do this. Encodec is literally what they are looking for. Encoder decoder quantization. That is just encodec, a model that Facebook made, or Meta made. Basically, you send this through an encoder, and the encoder is a bunch of convolutions. So if you're curious on how the encodec part works, I made a video on encodec, or check out a video on encodec. I it's a lot more to explain, but basically you send this through a convolutional neural network that is 1D, and it'll output a new representation of the audio, which is of shape, uh, this would be H in R of T by L. So basically your F of S goes to L, and your and T is just the number of frames you have. So yeah, that's your output representation. And this is your encoded representation. Basically, you have this really long audio and you just need to compress it in some way. So that's what your encoder does. And your encoder, like I said, just a convolutional neural network. Oh, my mistake. T is not just your sequence length. Well, T is your sequence length, but L is not just the encoded representation. No. Whenever you have a convolutional neural network, you send this through the CNN, and you get out. So with an image, you give it your image here. You send that through a CNN, and then it outputs this feature stack here of 2D uh, encodings. So in this case, you give it your 1D audio, and it will output a 2D representation of that. So a 2D feature stack. A feature stack of 1D audio frames. So basically, you encode this, and you extract the features. So each convolutional layer will probably expand the number of features as you decrease the actual size of the audio. So this will output the feature stack, which looks like this. And this will be of shape T by L, where L is the encoded, it's the compressed size, and T is the number of features. Yeah, so L is your feature size, T is the number of features. and this is just h. So I will change the shape of this to just stack them. So this will be t by l, and this is h in r of t by l. So now we're in r as opposed to -1, 1. So then what you do is you quantize this. So quantization, or you can quantize this through a process called residual vector quantization. So basically, you look at each part of t. So you look at each encoded representation, each feature. So you look at each feature and you want to quantize that. And the reason you want to quantize that is because transformers work with discrete data. So if you try to model this data, you're kind of having the model predict continuous data, which isn't what it was made to do. It was made to predict discrete token data. This is not discrete token data. It is in a discretized looking form. It is not discrete data. So you need to turn this into discrete data so that the transformer can model it through its autoregressive decoding process, because transformers work on predicting. Um, it works on predicting if you have a vocabulary, it predicts one of the tokens. So it basically um, predicts over your entire sequence which word comes next, and in this case, it'll be which residual vector comes next. So to do this, let's say we have a vector. So we have a vector here. We'll call this x, and this is of shape L, so it's a vector of length L. And what you do is you create a table, and your table will be of shape L by, let's just say Q. I will say n. So basically, this is a table where you have n vectors of shape L, like that. And what you do is you take your x, so you have x, this is your vector that you want, this is your continuous vector, and you look for the vector that is closest to x in the table. So maybe x is 1, 2, 3, and maybe we find a vector that is closest to x. So just use L2 distance, or you just use a similarity metric, and use a distance metric, and you can just use the L2 norm for that, or the Euclidean distance for that. So normal Euclidean distance. From all the vectors to this vector, you find the one that is the smallest, so which one is closest to this. And let's say we have a vector that's 1, 1, 1. And let's say this is the closest vector in our table to x. You then create, say, x. Let's label these 1, 2, 5. So you then create a new vector. Let's call this x prime, which is equal to your old x. We'll call this t1. So your old x, x minus the vector from the table. So this was vector 1 from table 1. So this is equal to 1, 2, 3 minus 1, 1, 1 minus 1, 1, 1, which is equal to 0, 1, 2. So x prime is now equal to 0, 1, 2. And we now have, if we just had a single table, we would use this vector as our new representation. So this is t1, 1, t1, 1, and this is our new vector representation of x. This is the closest thing we have given a single table to x. And this is now a discrete representation because we can just predict we can just look at our entire table and say, if you think of this as a vocabulary, then this would be the quote word we're predicting. Instead, this is going to be our residual vector that we're predicting, or the vector that we're predicting, and it's a discrete form because you're predicting one vector in a table as opposed to something in a continuous space. Now, this is good and all, but it's not very close. So instead, you can create another table, and and you can do this for as many tables as you want. So let's say this is also an n by L table, and I will add the same number of vectors in here. So 0, 1, 2, 3, 4, and 5. Now, what you do is you look for the vector in table 2 that is the closest to x prime. Let's say we have a vector that is 0, 1, 1. So now x double prime is equal to x prime minus t2. Okay, I'm going to move that vector. Let's say it's down here. Let's say it's 5, 0, 1, 1. So x prime minus t2. Then this will be equal to 1, it'll be this vector here, 0, 1, 2, which is the residual from the first table, minus 0, 1, 1, which results in 0, 0, 1. So now we basically have two vectors, 0, 1, 1, 1, and another vector, 0, 1, 1. And if we add these together, then we have the closest representation we can get with our two-table discretized representation. So this would result in 1, 2, 2, which is a lot closer than just having a single vector. And if you add another vector, maybe it becomes closer and closer, but it's kind of arbitrary. Basically, we now have a discrete representation of this, which looks like 1, so vector 1, and 5, vector 5. So this is our new representation for x, and we'll call this h. So h is our discrete representation, and you can also expand h to be a matrix. So this will be vector 1, which was 1, 1, 1, and then vector 5, which was 0, 1, 1. So yeah, that's just the expanded form of this. If you instead look at the indices in the table, you take the vectors here. So yeah, this is the new representation of x, and it's a discrete form because you can predict one token in your table. So that's the idea, and that is what we do here. So I'm just going to copy this down here. Copy it down to a new page. Great. Okay. So what you do is you send this through your residual vector quantization, and this gives you an output shape of, well, it'll be T by L for every codebook or for every table you have. We're not going to be representing it like this in indice form. This is what the model will predict. We're going to be representing it like here in token form. So each of these is like a token you would put into a transformer. So this is T by L, and this will be, say, N1. So NQ is the number of codebooks we have, and in this case, I use 3 codebooks. So we would have 3 different versions of this. So N2, and then T by L, which is N3, N3. So you quantize this into 3 times, and N2 is just it's just what we had here, table 2, and then N3 is just a third table. So you'd have a third table modeling this residual here. And the inverse transformation is pretty easy because you just add the vectors together. So now you have this discrete representation that you can model. And what they do is they need to flatten this. So to put this into a transformer, like we now have a sequence that is of shape T by L by N3. Basically what they do is they flatten this to T N, or yeah, N3. We'll call that NQ. T NQ. So they flatten it on that by L. So this is combined. And the way they combine this is by stacking the vectors, the quantized vectors. So you take the first vector from each of these, and then this becomes the first part of your sequence, like that. And this represents the first, so before quantization, this represents the first part of your audio stream. So the first continuous part of your audio stream is represented by these three vectors, these three discrete vectors here. And you can easily get the reconstructed version of your audio stream by just adding them together. So this is the reconstructed version of this here, this continuous vector here, by just adding these together because of how residual vector quantization works. You then get the second set of vectors, so like that, and this will be the second part of, or the second set of elements in your sequence. So this is now your sequence that you're going to throw into a transformer, which is of shape t. So this is t times nq. So that would be nq is equal to 3. And you have that t times, and then each of those vectors are of shape L. So we now have a representation of the audio in a discrete form. You can also, so you can easily reverse this to get your, so that the model, you can easily reverse this so that the model can make predictions. So if the model made this prediction here, so if the model was predicting these tokens, you can reverse this process by summing up these, and you'll get out your sequence of shape t by L, your continuous representation. So this would be h hat, h hat. So h hat is your reconstructed version, let's assume like an LLM predicted this, or a transformer predicted this. Then you can get your output sequence if you sum all these vectors together along their quantized forms, and then you send them through a decoder. And if they're using encodec, then the decoder is already trained, and this will give you your output sequence, which is of shape, your reconstructed output sequence, which is of shape x and -1, 1, and it's d by fs. D by fs. So yeah, that's the whole pipeline for encodec, basically. So this is basically just encodec with 3 residual vector quantizations and flattening this. Now, what they do is they take this intermediate representation, and then they throw that through a transformer, as you do. And they make predictions and then send it through the decoder. And that's how you would get your output audio. So let's go to how they do that. So they do that here through this. They have a 2-stage pipeline. So they call this the global transformer, and then they have a local transformer. Yeah. So you have your global transformer and then a local transformer. Everyone's favorite model. A little spelling mistake, but yeah, they have these 2 stages, and let's see how each one works. So we start with a sequence of tokens. Now this token sequence is going to represent the speech, and we're going to want to predict that speech. So we have this token representation of the speech, like so. And this first part is going to be nq is equal to 3. So this first part is the discretized form of the first part of the sequence. So in continuous form, this would just be 1 token. And you represent it in continuous form by adding them up. So add them up, and you get your continuous token again. So this is your continuous token at time t is equal to 1. And then you have your second set of features, your second set of tokens, which is t is equal to 2. This is nq is equal to 3. So this is L by 3. This is L by 3. That's the shape of this. And I mean, I've broken them up, but this is just one continuous stream of tokens, like in a normal transformer. And yeah, so you just have this continuous stream of tokens, and broken up by 3s, where each triplet is your discretized set. So I'm just going to stack them. So if we stack them like this, then you add them together, So you add the triplets together to get your continuous representation of each of these vectors, or of each time step. So each time step, t is equal 1, t is equal to 2, is added together. So their triplets are added together to get the continuous representation. And you get your output sequence. So this is t by L, or t times nq by L. And you get your output sequence, which is t by L. So that would be your first vector, that would be the second vector, and you do this for your whole sequence. So you now have these tokens which represent the entire sequence in continuous form. So you're basically unquantizing it. You then throw this sequence through a global transformer. So this is your global, I'll call this GT, global transformer. And the global transformer will output, so just a normal transformer style, it'll output another sequence of L by T. And each of these tokens is an encoded representation, so it's a transformed representation of that time step. So at time step 1, we now have a transform representation of that, or yeah, of that time step. Of that time step. So that, or rather of that part of your sequence length. So that's just encoding it. Then basically what we need to do is we need to, so in normal transformer fashion, you need to say, given this first token here, so given the first part of the audio, we need to predict the second part. And given the first and second parts, you need to predict the third part. So they do that by, so let me expand this. So this would be the first this would be the first part, this would be the second part, this would be the third part. And they do this by taking the token, so you can see that here. They take the token and they basically, so they add this to a start token. So you add it to a start token, and you send this through a local transformer. So the local transformer is basically going to predict the three, so this vector can be decomposed into its three discrete residual vector quantization vectors. So basically, this local transformer is going to take the token at time t minus 1. So if this was time t and this was time t minus 1, it's going to take the token at time t minus 1, and it's going to use that to autoregressively predict the three the three vectors in quantized form. So it takes the start token, and it'll predict the first quantization representation. So in this case, they call it Z. So this would be Z1. And in normal autoregressive fashion, you would add Z1 to your sequence, but they also add the continuous representation here, so the output of the global transformer. And basically, this is just guiding this to, this vector here is just guiding it to produce the next vector. So they add that to Z1, as shown here. And then it predicts Z2, Z2. And then you add Z2 to the sequence, and then it predicts Z3. So normal autoregressive fashion, and now you have your three vector parts here, which would go right here. So this would be Z1, Z2, Z3. Then you do this again for the next part, for the next set of vectors. So basically, your global transformer processes the entire sequence up to the current time step. Of course, you have masking and stuff, so that doesn't look ahead. But basically, it looks at all tokens in the past. It encodes all those tokens to a single, so it like encodes all that information to this single guidance token. And using this guidance token, you have a local transformer predict the three discretized vectors of the next set here. So you would have another set, another triplet here, which this local transformer predicts. And that's what you can see here. So you have your global transformer, it takes in all of your sequence, It then outputs a single vector, so like this, and the local transformer does an autoregressive prediction of the next part of the sequence of, so in continuous form, this would be a single vector. In discretized form, this is 3 vectors, so the local transformer is just doing that. And like I said, the reason you discretize it is so that this can be autoregressive, so this prediction here would be a distribution over your table, so 0, 1, 2, 3, 4, 5. So if we go back up to the table here, and this is our table, then it would be some distribution over that table, like this, over that table, so that you can make this autoregressive prediction. And then you just do your normal autoregressive predictions with the local transformer. And notice, we couldn't do that with the global transformer because the output of the global transformer, if we just had continuous representations, you can't do autoregressive modeling on continuous data. So that's why you need to discretize it so that it can do this prediction here. So yeah, I mean, that's all they do. They just send the entire sequence through, and they do autoregressive prediction with that with a local transformer. So nothing too special. It's pretty simple. Now let's look at how they construct the data, because that's another really big factor. So if we look at this, you can see that they construct the data by just appending everything together. So assuming you can discretize your data, then you can just throw it through the transformer. So instead of just giving it the audio, you throw it through a transformer like you're doing in context learning. So you give the transformer the start. So in this case, this is text to sound. This is a text to sound task. So you give it the start token and end tokens, and you give it basically your task type. So you're like this. So you tell it what its task is. So in this case, its task is a sound task. So you just encode that somehow. You just use like a set of tokens that tell it it's a sound task. Maybe just one token, one specific token saying this is a sound task. You then give it the text start token. So just some special token, and then you give it the text sequence. So the text sequence is just going to be a sequence from a large language model, which is just a set of tokens. So that's easy. Then you add the end token, saying that's the end of the sequence. And all this is just context. Then you add the audio start token, which is then when it starts doing autoregressive decoding. And it decodes it autoregressively decodes the audio sequence, and then you give it audio end, telling it to end the sequence. And you can just train this using normal transformer behavior in parallel, using this format. So basically what you're doing is you're giving it the context here, and that is your audio output, along with the task type. So sound task, is it music task, is it voice task, something like that. So it's very simple. Literally all you're doing is appending everything together, giving it a bunch of context, and then allowing it to decode some sort of audio according to the targets here. So that's all they're doing, and these are the contexts here. So assuming you can encode the context, then this works well. And they train it on a bunch of different tasks, and it does pretty well. So if we look here, I mean, it does well. I think these were the baselines, the baseline best models. So yeah, I mean, it's very competitive, and it outperforms in a lot of the cases. So yeah, it works well. That's what we like to see. And if it works well on a lot of different tasks, then I mean that's what you usually like to see in stuff like a language model. Um, yeah, so they also have fine tuning. So if we look at so an overview of the performance evaluation of UniAudio fine tuning, it does pretty well with fine tuning as well. So if you take the base model and you fine tune it on a new task, then you would expect it to do well. And it is competitive or performs better. So it's a very competitive model with fine tuning and just training from scratch. So this is always good to see. And yeah, that's the entire model. It's very, very simple. It's just take your sequence, give it the context, give it the task type, have it decode the audio, train this on a bunch of different audio tasks, and we're good to go. That's all they do. Yeah, it's cool to see that it works so well, and I love how it's open sourced. But I just kind of wanted to talk about it because it was a very interesting model that does quite well in a lot of different tasks, and it'll be interesting to see. It's interesting to see how good it does on such a simple training mechanism. But I guess that's just how the transformer works. Just train it on a ton of data, and it works wonders. So yeah, that's the model. Yeah, go ahead and check out the demo. Go ahead and check out the code. Um, it's all there on their GitHub page called or under UniAudio.